We studied about the sampling theorem. In the sampling theorem, to understand the Nyquist rate and aliasing is very important. Here shows some examples for sampling. So if we talk about the XCT continuous signal should be a band limited one. The definition for the band limited are shown here, that the maximum frequency of the XCT is limited by the omega m. If a frequency is larger than omega m, it should be 0. And the sampling frequency is defined by this way. Ts is sampling period. 2 pi over Ts is defined as sampling frequency. The relationship between the maximum frequency of a continuous XCT and the sampling frequency are shown here. This is called Nyquist rate. The half of the sampling frequency is called sampling rate. The sampling rate should be larger than the maximum frequency component. That's the Nyquist rate conditions. Sampling frequency should be at least 2 times faster than the signal bandwidth. Signal bandwidth at this moment is omega m. So omega s should be at least 2 times faster than omega m. Then, if it satisfies the conditions, XCT can be reconstructed by the sampled signal. Okay, the sampled signal can reconstruct the continuous signal by low-pass filtering if it satisfies Nyquist rate conditions. To understand the sampling, I would like to show you a practical example. Here is a sinusoidal signal, and at this moment, sample frequency and the signal is the same. In that case, sampling occurred at the same point. It seems like DC signals. So at every sample has the same value. So it is looks like a DC. Keep in mind, if a sample frequency is equal to the signal itself, it seems like a DC component. It's a DC means a 0 frequency. Okay, if I taking sample per every period 2 times fast, it means that the sample frequency is 2 times faster than original sinusoidal signal. So sample first sample and second sample, and first sample and second sample. Every period we have 2 samples. Okay. In these cases, in some offset value, this can be happen. So every point sampled 0. So is that possible to reconstruct the original signal? It's not that easy. Okay, it depends on the offset. Offset, if it is given this kind of offset, it's possible we can reconstruct that one. But offset is given like that. So look at here, every sampling point is 0. So this seems another DC component. Looks like that. So keep in mind what does that mean. And if we increase the sample up to 4, then first, second, third, and fourth samples, and first, second, third, fourth, like that, repeated. So this one is 4 times faster than the signal. The sample frequency is 4 times faster. So in this case, if you change any kind of offset, signal can be sampled properly. Okay, so even though in this case 0, 1, 0, and -1, so we can reconstruct by use of these data. Okay, I talk about that in certain point, as I talked to you, that this satisfies the sampling Nyquist rate. I mean that it's a double times faster compared to the original signal, but in certain case, it's not possible to reconstruct the signal in a certain offset cases. Okay. I hope that you get some idea that what is the sampling. It's the maximum frequency is omega m. At here, that this signal has the specific frequency. And in these examples, I use a frequency of it's normalized 1. So frequency period is 1. So it is 1 Hertz. So the signal is 1 Hertz. Sample frequency at this moment is 2 Hertz, and this one is 4 Hertz, like that. I show you that the 4 time cases, we have 4 samples for each period. So period is starting from here to here. So 1, 2, 3, 4 sample, and the next period is 1, 2, 3, 4 samples. So every period we have 4 samples in this case. What about here, that if we're taking the double of that one, that's the Nyquist rate. In the Nyquist rate, we have only 2 samples per period. So every period 1, 2, and the second period 1, 2, like that. And if we're taking the same as the signal frequency, it means that the sampling frequency I equals to the maximum signal frequency. In that case, it seems like a DC component. So this is the sampling process. How we interpret this behavior, as I talked to you that the omega s I equals to omega m, it seems like a DC. So we can think about by sampling, the frequency axis is folded by every multiples of Nyquist rate. Any multiples of sampling frequency of the XCT, it means that every integer multiple of omega s can be understood as a DC component. Okay, I mean that here shows that this is DC, but this one is a sampling frequency. This is the second times the 2 times sampling frequency, but in the spectral domain, this is DC, this is another DC, this is another DC, like that. Every omega s is folded back like that. Then this one becomes the maximum frequency. Okay, you can folding this one up to here, and this one is also folded here. So every signal is folded like that. Okay. Then we can understand the aliasing effect. Here shows that another example. Here is a sampling frequency is 10 kilohertz, so the Nyquist rate is 5 kilohertz. So here the blue curve has a frequency is 2.8 kilohertz, but the red one is 7.2 kilohertz. Compared to the Nyquist rate, the 2.8, it means a blue one satisfied Nyquist rate, but the it is switched. Red one is a 7.2. 7.2 kilohertz doesn't satisfy Nyquist rate. But if you're sampling with a 10 kilohertz, that point, you know that exactly the crossing point is sampled like that. So 2.8 and 7.2 kilohertz has the same sampling point and the same value at the 10 kilohertz. So we cannot distinguish between the 2.8 kilo and the 7.2 kilo by use of 10 kilohertz sampling. Okay, that is aliasing. We didn't distinguish between these two frequencies. Because of this 7.2 kilohertz doesn't satisfy Nyquist rate. By folding, you may understand that by folding the signal, the 2.8 overlap with the 7.2 kilohertz. It means that this was DC and this one is omega s. Okay, actually the frequency, I think this is better to express sample frequency fs. So Nyquist rate at this moment is 5k because sampling frequency is 10k. Okay, and 2.8k is around here. So this is 2.8k. And this distance 2.2k. So that's the location for this frequency component at here, the blue one. And 7.2 kilohertz corresponding around here. 7.2 kilohertz. That's this distance is 2.2k. That's the 7.2k, and this distance then it should be 2.8k. But I talk about that this is DC and this is sampling frequency, but by folding concept, as I talked to you that here this is folded by, means that by folding this one becomes the DC, another DC, then you can think about the folding mechanism like this one. This one is a DC, and here is a 2.8k. Maximum frequency is 5k. Okay, this is 5k. Okay, from here, this part is folded back. So this is 5k, and back to DC. Okay, this is a 10K. This is 5K, and this one is a 2.7K, 7.2K, sorry, 7.2K, and around back to here, DC. Okay, this is a folding concept. If you fold back, this spectrum stretched out, but you can fold back, then 7.2K is folded at exactly the same point of 2.8K. Because of that, we cannot distinguishing after sampling. So that is the aliasing occurred. So that is the basic idea for the aliasing that is explained over here. And if a signal satisfies the Nyquist rate, it should be looks like this one. In the spectral domain, the maximum frequency should be less than the Nyquist frequency. Then it satisfies the Nyquist rate. But it is undersampled. It means that it doesn't satisfy Nyquist rate. We call that is undersampled. Sample frequency is too low compared to the maximum frequency. This is maximum frequency, but the Nyquist rate is less than that one. Then aliasings are occurred. If aliasing occurred, we cannot reconstruct the original signal because the spectral is spectral domain signal is damaged, so we cannot reconstruct that one. If signal satisfy the sample Nyquist rate, we can recover the original signal without loss. So to make it safely sampling, we need to limit the bandwidth of the signal. To limiting the bandwidth, we are using the anti-aliasing filter. The maximum bandwidth is limited by this anti-aliasing filter. So before sampling, we have to apply anti-aliasing filter to avoid this aliasing phenomena. And from the discrete signal, we need to reconstruct the continuous signal. In that case, we are applied in reconstruction filter. That is, we talk about this kind of process. Sinc function is convoluted and summing up. Then we can reconstruct the analog signal. That is called the reconstruction filter. So this one is applied to digital signal to generate the original analog signal, that continuous one. Okay, so both of the anti-aliasing and reconstruction filter should be implemented by analog filters. Okay.